Good morning, everyone. My name is Shiva Krishna. I am from Institute of Aeronautical Engineering, Hyderabad. We are dealing with the subject of space dynamics, aerospace dynamics. So we are in the chapters of multiple degrees of freedom. So in that subtopic of frequency of mass and spring systems. So we are going to see about the how the spring mass system will be going to be checked. We can able to find the spring mass system vibration and how we can able to achieve this natural frequencies and modes of this particular natural frequencies of this particular 2 degrees of freedom. So we have been already seen about the what is the degrees of freedom and what is the multiple degrees of freedom and what is meant by natural frequency and how we can able to solve with the using of this natural Fourier series as well as in using of this Laplace series. So now we are into this mass as well as spring system, frequencies of mass and spring system we are going to. So here it is an example by using of this 2 degrees of freedom. There is a two masses is there and two forces are there here. So here is the force 1 and force 2, right? Which is having the displacements of x1 and x2s. So now we need to find the natural frequencies of this given problem as well as this mode shapes of this spring of the given mass spring system, which is constrained to be moved into the vertical direction, which is under this y direction, okay, y negative direction, okay. So now we have these two solutions for this. So here it is we are having this with the Newton second law of motion. We are having this force 1, force 2 we have taken as this as a zeros only. Here there is no force we have been applied. So we have been taken as zeros only. So here it is the force 1, force 2 has been taken as 0. So here it is the acceleration of masses we have been taken. So here it is the max, m into x double dot and 2k. Here it is a 2k1. Here it is a k1 and k2 of this one. 2k of x2 minus of k2. Here it is so reaction will be going to be happen. So if we are taking only single degrees of freedom like this, so m1 we have been taken, which is force applied. There is the acceleration we have been applied. So we have been applied acceleration. So we have been taken as a m1 into x1. So which will be going to be moved, which is in the direction of here. Okay, right this. So we have been taken as 2k x1, 2 times of this k, 2 times of this k into x1 distance we have it will be moved, and this spring which will be going to be moved again towards the reaction forces. Towards the reaction forces means which will be going to be negativities. So negative force we have to be make it as, so by using of this k2x, k2 of x, we have been taken as k of into x2 we have been taken as reaction forces. So we have been taken as negative here. Same as this we have been taken as m2 here. So here we just using the another bar which is m2. In this we are adding the force 1 here. Here it is the force m3 will be going to happen. So here it is the another force is going to be make it as a k2. It is a k1 will be going to be acted in this. Here it is the m2. This we are dealing with. Okay. Now which is going to be moved as this same. So here we are having this mass into acceleration of m2, mass into acceleration of m2, and k1x which is going to be towards this direction. So towards this direction which will be going to be pull back, which is going to be pull back. So we have been taken as minus kx1, okay, minus kx1, and it will be going to be add this one k1 to k1 into x2 direction we will be going to pull, right? So there is a forces we have been taken as 0 only. There is a harmonic forces we have been taken. So that will be going to be discussed later again. If there is a force which will be going to be called as another multiple degrees of freedom, and by assuming this harmonic solution which will be taken as x of I of t, x of I of t, which will be going to be taken as x of I cos omega t plus psi, omega t plus pi. Here we have been taken as I equals to 1 and 2 like this, 1, 2, 3, 4 like this. It will be going to move, right? So which will be taken as I of x of I into cos omega t into phi. Okay, now we are into this I equals to 1 and 2, right, which is going to be 1 and 2 here. So now the frequency of this equation can be obtained by using of this matrices form. So we are having the minus omega square minus m into omega square plus 2k by using of this, and minus k2 into the second element, and here it is the k2 as a next element. Here it is we have been written, and plus 2k. Here it is we have been taken as m omega square m minus omega square plus 2k we have been taken here. So here, which is case has been taken diagonally and masses has been taken into this diagonally here. So now we are into this equation form we can able to obtain by using of this harmonic motion, and the frequency can be obtained by using of this matrices form. So here we have been taken into this summation to the both sides as a m into x1 plus k into xi we have been taken into one side, and the same type of equation to the second equation we have been taken into this minus omega square plus 2k we have been taken at this side, okay, as it is here. So just we have been taken swipe to this right side, okay, just we have been taken like this. And now if we multiply together, like AD minus BC we have been taken as AD minus BC if we are taken, then it will be going to be omega square of to the power of m square to the power of omega square omega to the power 4 and 4 of k to the omega square plus 3k square, it will be going to be 0. So if we multiply together AD minus BC that we have been taken, so it will be going to be like this. This equation will be going to be formed. So now from this equation, let me solve using of this equation. We know that minus b plus or minus under root of 2ab minus bc by 2ac. By using of this roots equation, we are going to proceed 1 plus 1 minus equation. So just we have been taken as a, b, c equals to 0. So here it is under this equation we have been taken. So under this we have been taken minus 4bc. So minus 4km we have been taken. So omegas we have been taken as a constants only. So just we are avoiding this one for our convenience purpose to make this as a particular frequency analysis. So just we have been taken into this depth equation. After that we have been taken into this natural frequency equation, and then we have been taken into this roots equation. After this natural frequency will be going to come. So first root it will be going to come as omega 1. Omega 1 will be going to be minus 4km, that is BC, plus we have been taken minus into minus plus we have been taken minus BC plus or minus plus minus we have been taken first under root of 2ab. So here it is the a equals to m square, 2 into we have been taken m square, and 3 is there directly. So 2 into 3 we have been taken 16 and squares we have been taken, right? So just we have been multiplied all these together minus 2ab. So we have been taken 4 into 3 12 plus here it is it will be going to be 16 k square m square and minus 2 bc we have been taken 4 into 3 12 we have been taken like here, okay. Under root we have been taken half here or the m here we have taken. So here it is 2ac we have been taken 2 into a equals to we have been taken as m square, okay. Here it is a k also we have been taken as some omega, okay. The constant we have been taken. So we have been taken into this under root of k by m is a natural frequency of 1 we have been found out. The same way if they are taken as a positive, then it will becomes under root of 3k by m, it will be going to be omega 1 omega 2, okay. Omega 1 omega 2 for the natural frequencies, right? So now we just go to the next mass spring equations. From this we just know that roots of this particular equation. So just we have been found out the roots, then we have been know to that from this equation mass spring 1. So r1 equals to here x2 by x1. R1 equals to x2 by x1. So what is x1 here we have been taken? X1 is nothing but here we have been taken into this particular thing. X1 we have been taken here. Equation 1. Okay. So here it is the minus m1 omega square plus k1 plus k2 by k2. It will be going to be we have been taken as a minus k2 we have been taken outside here. So here it will become small 1 by chances. Okay, it will be going to be 1 by of this one. So here it is a k2 by m2 omega 2 omega 1 square plus k2 plus k3. So it will be going to be equation 1. Equation 1 we have been taken as r1. So root 1 will be going to be, root 2 will be going to be like this. Same thing we have been taken for this x2 by x1. x2 by x1 we have been taken. So x2 equals to nothing but here we have been taken as m1 into omega 2 m1 into omega 2 square plus k1 plus k2. What are the connection is there? whatever the connection is there, we have been taken into this picture. Whatever the connection is there from this picture. So omega frequency here it is omega 2 we have been taken. Okay, k1 plus k2 we have been taken. Here it is a k2 plus k3 we have been taken. Okay, k2 plus k3 we have been taken. So just we have kept this as a x2 of square, x2 of x1 of square we have been taken. So it will be same thing we have been taken x2 of square. It is a one mass system, mass 1, mass 2. Okay, there is a mass 1, mass 2 system. Mass 1, mass 2 system is connected here. So it will be going to give the k2 by omega k2 by m2 omega square of 2 omega 2 plus k2 plus k3, which will be going to be second equation. Now amplitude is given by which will be going to be m1. It will be going to be taken as minus of m1 into omega 1 plus 2k by k equals 2, which will be taken as k into, just we have been taken into this 1 by of this one, 1 by of this one we have been taken. So 1 by of we have been taken directly. So it will be going to give the minus 1 plus 1, which will be going to give us this. Okay, just be following this previous equations. Now what is the frequencies? What is the frequency we have been taken? X bar of 1, x bar of 2 of t's. So just we have been multiplied of this with the time function. With the time function we have been taken, and which will be going to be using of this x1 of cos omega t plus phi and r of x1 of 1 cos omega t 5, which will be give the first mode. The same way we have been taken omega 2, which is a natural frequency, we have been replaced. So that will be going to give the natural frequencies. Then it will be going to be mod 2, second 2. Okay, mod second mode. And now which is in this first mode, second mode, we have been taken into these inverses. So just we have been taken as bar, above the bar we have been taken. Then we have been written omegas. We have been taken omegas into the form of mode shapes. So here we have been replaced omegas into this under root of k by m, under root of 3k by m we have been taken. Just we have been replaced with this. Okay. Natural frequency of these modes we have been taken, first mode and second mode, just we have been replaced with this. So this is the first mode. With this we can able to write this one first mass, second mass and springs is connected, and which will be give the natural frequencies about this. Okay, so just we have been given a forces above this, the forces we have been taken given above here. So again there is a reactions will be going to be towards like this. So it will be going to be, we can take it as a some mass are connected into this parallelly, into the system. And the same way if you are taking this mode 2, that is a 3k by m if you are taken, then it will becomes like into this triangular shape, which is under this sine wave form. So sine wave form it will be going to be happen. So which will be having 3 nodes. So one node, second node, and third node. So it will be going to be mass at 1, mass at 2, which will be the node 1, node 2. At this center, which is crossing at this 0, which will be taken as node. So here in this no node will be there, no nodes will be there. In this one node is there. Okay, in this one node is there, which is under the positive condition, second node. So now we just going to find out this as this. It can be seen that in the system of vibration first mode, the amplitude of these two masses are remaining same. In the first mode, the masses will be same, and this simplifies that there is a length of the middle spring of the remains constant, and thus the motion of this mass and 1 are in the same plane, which are taken into this mass 1. There is a frequency 1 if you are taken, then the masses as well as the length will be going to be same. And if we are taken this as a second mode, then it will be going to be length will be going to be extension. There is a spring will be going to be extended, and there will be some vibration will be going to be happening to this. Okay, thus the motion of this one mass 1, mass 2 are in the same phase. And which is under the second mode we have been taken. When the vibration of the second, when it comes to the second mode, the equation below shows the displacement of these two masses have the same magnitude with the opposite signs. So here it is a mass 1 and mass 2, which is the minus 1, minus 2. Minus 1, minus 2 have been happened. So which is with a different magnitude it was happened. So displacement of these two masses have the same magnitude with the opposite signs. Thus the motion of this mass 1 and mass 2 are out of the phase. So out of the phase it has happened. So at this middle point of the spring will be remain stationary. Such point is called as a node. So at this middle point, it will be called as node 1. Okay. By using of these frequency mass spring system equations, we just follow this x1 equals to x1 of t, x1 of which is mass 1 and which is mass 2. We can just replace this with a x1 of t, x2 of t we have been taken as x1 of cos omega t plus phi. We have been taken x1 of t cos. We just replace with this cos of omega t plus phi, cos of omega 2 plus phi we have been taken. So just we have been replacing about this again into the form of under root of k by m, under root of k 3km we have been taken. And mode shapes can be expressed. Mode shapes can be expressed in terms of x1 plus x2. x1 plus x2 we have been taken. There is a mass at 1, mass at 2, and mode shapes with this plus sign, positive sign, and negative sign we have been taken once and second. So which is under this x1 of cos under root of k by m of t plus phi plus x1 of 2 which is a mass 2 cos under root of 3k by m of t plus phi, which is under the positive signature, and under the negative signature it will be going to be same with a negative signature. Okay. And force vibration analysis, in this we just follow this with this degrees of freedom of this under this external forces as written. So external forces we just follow the previously as a zeros forces, which is there is no damping forces. So here which will be going to be happen with the another force, external forces we have been taken, that is x1 and x2. If we are taken with the forces, then it what will be going to be happen. So at mass 1 and mass 1 2, mass 1 2 and mass 2 2, we have been just followed the equation from the matrices form, which is connected like this, mass 1 mass 2, which is 3 degrees of freedom we have 3 degrees of freedom we have been taken. So just we are finding the elements which is at mass 1 1, mass 1 2, mass 1 2 and mass 2 2. So which is connected with the springs here, and it is the extension of this axis which will be going to be happen with this acceleration of 1, acceleration of 2, and dash parts which will be going to be happen with the c11, c12, c12 and c22, which will be going to be velocity will be going to happen, which is x1 and x2, the same which will be having the spring system. So k11, k12, k12 and k22, and which will be having the displacement of x1 and x2, which will be going to give the forces equation. So from this consideration of external forces, we shall find the external forces with the using of this fj of t. We can able to write it as fj of naught e to the power of I omega t. We can able to write j equals to 1 and 2. Okay, where omega of this frequency, omega forcing frequency, we can write this steady state solution, which is x of j, x of t of j. We can write it as x of j e to the power of I omega t. Ij equals to, we can able to write it in terms of 1 and 2, which will be going to be later, which is as a x to the power of j. We can able to write it as complete equation into this whatever the matrices form we have been taken. We can able to write it in terms of x of ij of t. So where the x1 x2 are general complex quantities, that will be depends upon the omega system parameters. Substituting above equation into the first of twos. So substituting above these two into this equation. Okay. So we just omitted this equation into this form. So just general substituting about two equations into the first one, which is into the first and 2 and 3. 2 and 3 into 1 we are writing. 2 and 3 into the 1 we are writing here. So just we are obtaining here as a omega of square minus omega square of m11 I of omega c11 plus k11, which will be going to give as a element 1, and element 2 will be minus omega m11 m12, which will be same minus 1 2 1 2 1 2 will be there. Masses damper as well as k, masses damper k omega have been taken here, and just we are applying with these omegas, which will be I omega, and we are constantly giving this f1 and f2. So here it is the mass damper and k, m c k, just we have been combined together, and we are just adding with this minus omega square. So just if you go to this previous equation into this, just if you are multiplying all this equation and finding left over this one velocity is acceleration at this particular point. So just we find it m plus c plus k we have been taken, multiplying with this minus omega square of 1. Okay, minus square of omega 1. So just we are taking with this mass 1 c1 c2. So just we are representing node 1 node 2 node 3 and node 1 to node 1 2 and node 3. Here it is a 1 1, here it is a 1 2 and 1 2 and 2 2. So just we are placing minus omega square at these particular places, and x of t we have been taken as a complete solution. So completely we have been taken as x, that is the distance we have been taken at these particular places. The particular places multiplied by using of this displacement, and which will be give the f1 and f2s. F1 f2s we can able to get it by using of these forces. So here it is the 1 2. So 1 1 element, 1 2 element, 1 2 element again, and 2 1 2 2 element. So which will be going to be give the defining the term is called as a mechanical independence. Mechanical independence we are representing in terms of z of rs. Z of rs in the terms of I omega as a form. Right? So here it is the z of rs. Z of rs which will be going to given as one term. Completely this one term we are just giving as m square of rs, omega square of rs, and I of omega crs and krs we have been taken. Rs we have been taken as in terms of 1 and 2s. Okay. And now we are writing with this first equation z of I omega's x bar. So here in this term just we are replacing all this equation. From this all this equation just we are replacing mechanical independence as this the term. So all these terms which is 1 1 1 2 1 2 and 2 2 we have been replaced with these terms of z of I omega. Okay, z of rs of omega, which will be going to given as a first equation of this one. This is the first equation. And now we just all this equation of elements we have written in terms of z of rs. Okay, which is under this z of rs of I omega. Okay, which is z we have been written in terms of, okay, which we have been written in terms of omega square of mrs plus I omega crs plus krs. Okay, just remember this equation as a mechanical independence. So just we have been replacing all these things into this z of I omega of x bar t. Okay, x bar. So which will be going to be given as forces of north. Okay. Now where is this z of I omega t? We can able to expand this one. We can able to expand in terms of 1 1 1 2 1 2 and 2 2 in terms of z. Okay, in terms of z we have been represented, and independence matrices we have been written. Independence matrices we have been written in terms of all these one. Okay, just we are replacing all these elements in terms of z only. Okay, just which is called as a mechanical independence, and which is we have been written in terms of again 1 1 1 2 1 2 and 2 2 we have been just representing as a independence matrices. Okay, now the equation which will be going to be z of I of w equals to x naught will be going to be 0, and which can be solved by easily, and we can able to make it as x of dot we can able to write it in terms of x of dot we can able to write it as I w of inverse. Inverse we just represent in terms of 1 by z of I2, z of IW, just I omega we have been taken into this particular forces, right? And where inverse of this independence matrices is given by 1 by of all these things. Okay, z of inverse we can able to write it in terms of 1 by z of 1 1 I omega t, and z of 2 2 I omega 2, and z square of 1 2s we can able to write it, right? So we can able to write it again the forces one in terms of here as a 1 2 2 and 1 1, which will be replaced here, like into this b2, sorry, a b c d we have been written in terms of inverse, which is take into this x bar, x equals to we have been taken. Okay, x we have been taken, and x inverse we have been taken as 1 by of x ad minus bc, sorry, we have been taken as ad minus bc squares. Okay, and here we have been taken dbca, dbc we have been taken, Just we have been replaced all these things. We have been taken into this debt. Okay, debt we have been taken. Okay, mod and debt has been taken. All those things. And by using of this equation, we can just able to solve by using of this x of I omega t, x of 1 omega t. We can be able to replace it in terms of z of 1 2, z of 2 2. Just we are replacing with this of f1. So just we are writing again into the multiplication of this one. So z omega inverse we are replacing here and multiplying with this by using of this f naught. Okay, by using of this f naught we have been replaced. Just we are writing into this f naught into this equation by using of this multiplication of all this. So after this multiplication, we are again multiplying of this f naught bar. Okay, just remember again you need to solve it very cautious because it will be going to be mismatch as well as some multiplication errors will be going to be happens into this matrices form. If you are concentrated on it, that will be going to be happen. Otherwise, it will be going to be mess. Okay, so just we need to be concentrated and cool. We need to be solve this all this equation. It will be going to be taken some long time, but you need to be achieved very smoothly. And substituting of this equation into the below equation, which will be going to be solved with this of x of j of t, x of j of t, we can able to write it in terms of x of j e to the power of I omega equal I omega t. J equals to we have been taken as 1 into we have just seen previously also, right? And that is the spring mass system vibration analysis of this particular system. So here it is the equation 1 and the equation 2 are very important. You need to be considered for this solution for this as a force vibrations. The force vibration which is having the force 1 and force 2 which is distances moved. Distances moved. If you want again distance x dot and x double dot, if you want, then we need to be placed as a d by dt and d square by dt square. Just we need to be replaced for these equations, okay, which is for these distances for this above equation form, which is forces have been solved. And now coming to the multi degrees of freedom as a system, which is going to be continued as a next topic, which is modeling continuous system as a multiple degrees of freedom, and eigenvalues problem. So just we are following this one today. So modeling of a continuous system as a 3 degrees of freedom. So what is meant by multi degrees of freedom? And it is stated that before that engineering system was continuously are having infinite number of degrees of freedom. So if you take any propeller shaft or else any mechanical system piston or else rings or else connected rods, all these things we are not going to be seen as a single parts. So it will be connected to the number of parts. So if you want to work into any system, it will be connected to the other one. If it will take output from one side and it will go the input to the one other side. So if you are connected to this one piston rod, and if it is to and fro, if it is happen inside the piston, it will be moved towards the right and left it will be going to move. So it is the one of the degrees of freedom we can able to say that is the piston is moved means there will be going to be it will be moved to the right side and left side it will be going to move, right? So here it is the input will be into this x-axis y-axis, that is a multiple degrees of freedom we can say. So here it is the x-axis y-axis and there is a piston is moved towards the right side left side it will be going to move. It is called as a connected system, continuous system it will be called. Okay, the vibration analysis of continuous system requires solution of the partial differential equation, which will be quite difficult. So we are just not dealing with the partial differential equations because we are dealing with the at a time with this velocity, at a time acceleration, at a time temperature, at a time density. All these things we are going to be used into the partial differential equations. At a time, we cannot able to say there is a flight if it is moving or else any vehicle if it is moving. At a particular time period, the velocity or else temperature or else any viscosity, it will be not going to be constant. So each time it will be varies because of there is the idle condition or else there is a running condition. It will be varies as much as possible. So it will be not same as in the second to second. So just we need to be go for this partial equation because we are dealing with this each and every element there is a temperature, velocity, acceleration and density and more of the air breathing condition, air out condition. So all these things will be going to be dealt with in this partial differential equation. Once if you want any particular point acceleration or else deceleration conditions, which will be going to be dealt with this each and every subtopic like a velocity or acceleration or temperature, we are required into this partial differential conditions only mostly because it will be going to be having while the varying system, there is a variation will be going to be happen. So we are concentrating on this particularly. So we require only partial differential equation to solve this multiple degrees of freedom at a particular instances. So in fact, the analysis of analytical of the solution does not exist in the many partial differential equations. So analysis of these multiple degrees of freedom on this other hand, which will be required, solution of set of ordinary differential equation. It will be compulsory. We need to be learn about the ordinary differential equation as well as the partial differential equations as in the form of multiple degrees of freedom solutions. So which will be relatively simple, and hence simplicity of this analysis will be continuous system, often approximated, which will be multiple degrees of freedoms only. So as we said before, once if you want any solution, there will be particularly instance time. So there will be going to be happen into the variations. The variation will be able to solve by using of these partial differential equations only, which will be called as a multiple degrees of freedom. For a system having the number of n degrees of freedom, there will be n associated with natural frequencies, which will be associated with this mods shapes, which will be having own mod shapes. So each and every velocity, acceleration, what we say into the particular system in the flows, there will be each and every time there will be compulsory, there is a changes will be going to be happen. Say if there is a sun is having a daily routine of 5 o'clock, it will be not possible, right? Dial sun won't be comfortable exact 5:30, exact 5:20. So day by day it will be going to be changes according to the weather conditions, according to the nature, right? So same thing, it will be multiple degrees of freedom, which will be going to be happen to the every stage by stage according to the sunlight. If you say there is an example of nature, so there is a particularly ignition system to the offing of system, the temperature variation, hill up, hill down, all these things will need to be considered as ideal condition we're just dealing with, but we need to be considered for each and every type of period of these steps that will be called as multiple degrees of freedom. So each one having the mode shapes. So whatever the each condition we have been applied, that will be called as own natural frequency and both mode shapes, right? So different model methods can be obtained, can be used for the approximate continuous solutions, which will be taken as multiple degrees of freedom as a method of involving the replacing the distributed mass or inertia of the system by the finite lumped mass system or rigid bodies. So which will be going to be seen that is a finite element method or finite element models, which will be going to use this particularly to solve the multiple degrees of freedom. So it will be going to be used as a multiple lumped masses or else inertias of the particular system. So lumped masses is nothing but which will be connected masses and massless elasticity damping system of the members, and linear coordinates which will be used for the describing the motion of these lumped masses, such models as called as lumped parameters of lumped masses or discrete mass system, discrete mass systems we call, okay, DMS. Most simply we can call it as a DMS, which is discrete models. Okay, minimum number of coordinates are necessary to be determined describe this motion for the lumped mass system of rigid body. The number of degrees of freedom of this system will be naturally larger than this lumped mass system, which will be called as masses lumped using models, and higher accuracy will be going to be having higher results. Okay, so this is one of the example we have been taken as a 3-story building, which is as a floor as a masses. So mass 1, mass 2, mass 1. This is mass 3, mass 2, and mass 1. Sorry, that is a mass 1. So each and every floor we have been taken as a masses. So like in the people are standing, or else there is a fridge, or else a washing machine. Okay, the things we have been placed under the balcony or else home, which will be called as a mass. Okay, which will be simply called as a mass, which is approximately taken as a how much it can able to bear, that will be called as mass. Okay, complete mass we have been taken into this particular system. Some of the problems are automatically indicated the lumped parameters of this model as you see, like a mass 1, mass 2, mass 3. It will be shown as you see. For the example of 3-story building has been shown in the figure, automatically suggests there is a 3 lumped masses of this model, M1, M2, M3 we have been shown. It will be going to be seen to this particular picture. In this model, there is the inertia of the system is assumed to be connected or concentrated of these 3 masses system located on these floor levels. Elasticity of these columns are replaced by using of the springs. So these columns are K1, K2, sorry, this is a K2, K1, K2, K3. Okay, these are columns. There is a pillars or columns called as. So K1, K2, K3. If you are having any disturbances, it will be going to be observed, right? Which is elastic columns we have been observed. And this is the foundations. It is also can be observed. Foundation of this particular pillars we can able to observe. And once if it is happening any forces into this vertical or horizontally, okay, then there is a small movement will be going to be happen. We cannot able to see into the our naked eyes, but into the atomic level there is a continuously a small movement will be going to be happen into these particular forces. Another popular method for the approximation of continuous system as a multiple degrees of freedom involves in the replacing of geometry of this system by large number of small elements which will be called as nodes. We can able to call it as nodes, which will be connected like this. So each and every storage will be taken into the as a mass systems. Okay, and these models are can be done by using of these different modeling methods, and which will be solved by using of this ANSYS, ProE, and multiphysics. Multiphysics and different FEM softwares. We can able to use this to solve this particular storage building of Earth's masses and natural frequencies we can able to obtain. And these things are replaced by using of these masses and systems, and we can able to apply the forces by using of natural frequencies we can able to solve. And here it is in Newton's second law. We can derive this equation of motion, which are already defined previously also. And we have been replaced with rigid masses, which is the body of masses we have been taken, external forces we have been taken as a positive displacement, velocity of given with this rigid masses bodies. So these are all the small things. Just we have been connected with this all this mass 1, mass 2, mass 3, which is under this Newton equations. So we will be going to be stopped today by using of this one. Okay, we can able to solve. Okay, so today we just stop this one.
Like, share and subscribe. Hit the bell icon for more updates.